Just a quick note on that last example. The angles associated with potential energy, if you have a spring between two links, for example, in that previous problem, we had one spring at this corner and another spring at this corner of a triangle. And so in general, anytime you've got two vectors involved in a spring, you'd write the expression for the potential energy, or for the potential energy is going to look like k theta over 2 times the change in the first angle minus the change in the second angle, all that quantity squared. Now, because the angle associated with this vector never changes, this is just going to be a 0. And so that's why it reduces, the potential energy term reduces just down to this part. And the same for if I do this corner right here, I'm going to have theta 1 minus theta 1 naught. And those are always going to stay the same because the angle of this vector never changes. What that gives me then is, once again, I have an expression that looks like this that's squared for my potential energy. Sorry, there's a k theta over 2 out front. But this is the expression for potential energy, and sure, there's a negative here, but the squared takes care of that. And so it's kind of interesting how it works out that these just amount to something very similar, even though they're on different corners of a triangle.